So today we are going to start talking about the interference. Interference is nothing but the superposition of two waves. आपके पास में कभी भी दो waves हैं, अगर वो एक दूसरे के ऊपर में superimpose करेंगे, there will be some kind of intensity distribution, and that intensity distribution pattern is basically called as interference. We are going to talk about interference pattern of electromagnetic waves, which basically means that whatever we have done in the EM wave theory is basically now applicable here. So if you talk about interference of water wave, agar aapne water, let's say there is a pond of water and you have dropped stones at 2 points, of course there will be superposition and you will get some kind of distribution on the amplitude of the waves. But what about the interference in electromagnetic waves? What is it which is superimposing on the top of each other? आप कहते हैं ना आपके amplitude interference. If you say that you have two waves with one amplitude y1, second with y2, they will superimpose on each other and your resultant amplitude would be basically given by this. So these are basically, you're talking about the amplitudes. In the case of electromagnetic waves, what are these amplitudes? Amplitudes of what? Anyone wants to answer this question?
Electric field.
Yes. Our eyes are sensitive to electric field. And remember, the magnitude of electric field is 3 into 10 raised to power 8 times the magnitude of magnetic field. So whenever you are talking about the superimposition here, mainly that means we are talking about the superimpositions of electric field. So when you are talking about amplitude is given by this expression A cos omega t or A cos kx minus omega t or whatever is the expression here. So that means we are talking about the amplitude. Now A1 would be amplitude corresponding to y1 and A2 would be the amplitude corresponding to the second. So this now is the superposition of amplitudes of the electric field in this case, or the resultant displacement due to the electric fields here. Now, do we expect interference pattern if, for example, if you put two bulbs in the room in which you are sitting right now, we don't see any interference pattern, right? Why is that so? Can anyone answer this?
Ma'am, because there's a phase difference between the two waves.
The phase difference must remain the constant, right?
Yes, ma'am.
So that means those two bulbs, they are not the coherent sources. So for interference to happen, the sources that you are using, they must be coherent sources. If they are not coherent, what would happen? This phi that we are taking the phase difference between these two displacements or these two waves, this phase difference will keep on changing continuously and rapidly. अगर ये continuously और rapidly change होता रहेगा तो आपका जो resultant displacement है वो continuously और rapidly change होता रहेगा. And आप कोई भी, our eyes are sensitive up to a certain limit of टाइम, अगर उस टाइम फ्रैक्शन से ज्यादा रैपिडली अगर आपका इंटेंसिटी डिस्ट्रीब्यूशन चेंज होगा, we won't be able to detect it. So your sources of light must be coherent. You might have done already the Young's double slit experiment. In the Young's double slit experiment, what you do is that you have the single sources and then you put the double slit here, and on the screen you see the interference pattern. So your source is just one source. You are converting this source into two sources by division of the wavefront. You say that your wavefront will come over here, and then here you will have two sources basically on at this point. So you are dividing the single wavefront into two wavefronts. So in the Young's double slit, the interference pattern that you see on the screen is because of the division of the wavefront. In this unit, we are going to do it by division of amplitude, which basically means that we are going to talk about, for example, on a surface, if a light ray is incident, a part of it is reflected, a part of it will be transmitted or refracted, whatever you want to say the word here. Now, if let's say this film is of finite thickness, what would happen at this point? The light ray will be again reflected and it will be transmitted as well. At this point, when light wave is incident, again, a part of it will be reflected and a part of it will be transmitted. So the transmitted part will go in this direction and the reflected part will come here. So if you talk about ray 1 and ray 2 now, they started from the single ray here. And we are basically dividing the amplitude into two components. At this point, a part of the amplitude was reflected and a part of amplitude was transmitted. And at this point again, it's partly reflected, partly transmitted, and here also partly reflected and partly transmitted. Now the waves which are coming from ray 1 and ray 2, they will superimpose on each other and they will generate some kind of interference pattern. And this kind of intensity distribution that you see is basically because of the division of amplitude. बहुत सारे बर्ड्स में, स्नेक्स में आप जो कलर्स देखते हैं, दैट इज बिकॉज ऑफ दिस थिन फिल्म इंटरफेरेंस पैटर्न और वेज शेप इंटरफेरेंस पैटर्न. इन द थिन फिल्म there could be two type of thin film. One is the parallel thin film, जहां पे आपकी इसकी thickness है constant रहती है. The other one could be the wedge shape thin film, in which the thickness is going to change in one direction or other direction. अब रोड पे अगर पेट्रोल स्पिल कर जाता है and if it rains, then you see the very colorful distribution of intensity pattern on the road itself, and that is like again an example of the similar case here. So bubbles में आप जो colors देखते हैं, again because of this kind of interference, where the interference happens because of the division of the amplitude. The second criteria, and the first criteria is absolutely must criteria. Agar if your sources are not coherent, you won't be able to see interference pattern. But if you want the good quality of interference pattern, then your sources better be monochromatic. And again, this is not a must condition. The second condition, if they are not monochromatic, for example, as I said before, in the soap bubble, when light is incident, and that is basically the colors that we see is in the sunlight. And we know sunlight is for sure not a monochromatic source of light, but nonetheless, we see the color pattern there. So it's not as if we won't see the interference pattern if the source is not monochromatic. The only difference here would be if it is monochromatic, then you can better identify the bright fringe and the dark fringe, bright fringe and dark fringe. If for example, you are using white source of light, your fringes will overlap on each other. And then you won't be able to identify very clearly where the first fringe is ending and where the second fringe is starting, basically. So as I said before, and I'm repeating that again, condition one is the absolute must condition. The second condition is just for the clarity that your fringes have better quality. It's not a must condition for interference to happen. So we'll start from here, but before we go into any further, let's talk about something which is called as Stokes law. In the EM wave, we did Stokes theorem, which was the fundamental theorem of curls. And now this is Stokes law. It is not theorem. This basically states that, let me first write the statement of this law. It says that, and it is based on the principle of optical reversibility. And this law basically states that in the absence of absorption, we are saying that there is no absorption of light, then reflected and refracted light. We are saying that at the interface between the two surfaces, there will be either reflection or refraction, or even if both of them are there, that only though those two possibilities exist, there is no third possibility such as absorption of light. So if light is incident on interface, then only possibility is that it is either reflected or it will be transmitted or refracted. It will not be absorbed. So this principle says that if there is no absorption, then the reflected and refracted sorry, I should write it, refracted light will retrace its original path if its direction is reversed. In a very layman term, this is basically saying that if it's as if saying that you entered in the room through door, and then if you want to go back, you will go through the same path. This is what it in very layman terms says here. This means that, let's say I have an interface here. In this side of the interface, there is a medium whose refractive index is N1. On this side, there is a medium whose refractive index is N2. Now, let's say that when you go from N1 to N2, जब आपकी light incident होगी from N1 to N2, they will be partly reflected and partly this light will be refracted or transmitted. So I'm saying that if you go from medium N1 to N2, let's say that R1 is your reflection coefficient for amplitude. And T1 is your transmission or refraction coefficient. Now in the second scenario, let's say that rather than your light being incident in this direction, what if it is incident in other direction, which basically means that what would happen if the light is incident from medium N2 to N1. And let's say that if that is the case, if you are going from N2 to N1, and let's define again R2 as the reflection coefficient. And this reflection coefficient is for amplitude. And T1 as the transmission coefficient. Now we would like to know what is the relationship between R1 and R2 and T1 and T2. Sorry, this is T2. Are they similar? Are they different? So we would like to get some kind of relationship between R1 and R2 and T1 and T2. So let's say that here the light ray which was incident here, it was incident with amplitude A1. I'm saying that R1 is the reflection coefficient when you are going from medium 1 to medium 2. So what would happen? A times R1 will be the light which will be reflected, right? आपकी जितना इंसिडेंट है उसका आपका रिफ्लेक्शन कोफिशिएंट से आप मल्टीप्लाई कर दोगे तो दैट मच विल बी द रिफ्लेक्टेड लाइट. Here the transmitted light would be A times T1 because T1 is your transmission coefficient, and we said, as we said before, A1 is the amplitude of the incident light. So R1 is the reflection coefficient, so A times R1 आपकी reflect होगी. T1 is the transmission coefficient, A times T1 जो है वो अब आपकी transmit हो गई. Now let's talk about this law. This was simple. There wasn't any application of this law so far. Now this says that if there is no absorption of light, then reflected and refracted light will retrace its original path if its direction is reversed. Now this says that what if this AT1 was moving in this direction? What is if I reverse the direction of this one and the direction of this one also? Then this principle says that it has to retrace its original path. And this is basically based on time reversal and everything. So if it wants to retrace its original path, what does that mean? This means कि हमको वापस simply A मिल जाना चाहिए. There should be nothing else apart from that. Only we should get A in this case. So let's talk about now each one of these ray one by one. Let me write N2 slightly away. So this is N2. Let's first talk about this ray here. This ray is now incident from medium N2 to N1. N2 से N1 पे ये incident है. We said if you are going from N2 to N1, R2 इज योर रिफ्लेक्शन कोफिशिएंट। तो यहाँ पे अगर ये इंसिडेंट है तो आपकी जो रिफ्लेक्टेड होगी वो होगी आपकी 8 टाइम्स T1 R2, क्योंकि अब ये आपका एम्पलीट्यूड है इंसिडेंट का और इसको मैंने रिफ्लेक्शन कोफिशिएंट से सिंपली मल्टीप्लाई कर दिया है। So this will be the reflected light here. Again, a part of it will be transmitted also. Transmitted part here. If this is AT1, this is the amplitude of incident, and we said if you are going from N2 to N1, T2 is the transmission coefficient. So incident multiplied by the transmission coefficient. This much of this incident light will be transmitted into the medium whose refractive index is N1. So this is what would happen if we reverse the direction of this AT1. A part of it will be reflected and a part of it will be transmitted here. Now let's do the similar for the other one. For this second.
Can you please explain this law again?
So this law basically states that if there is no absorption of light at any interface, and what would happen in that case, आपकी जो light होगी वो reflect और refract या transmit होगी, right? सिर्फ दो possibility हैं आपके पास में, refraction की है और reflection की है. Now this principle states that अगर ये मेरी incident light थी and let's say R1 was your reflection coefficient and T1 was transmission coefficient, तो एक part इसका आपका reflect हो गया, एक part इसका transmit हो गया. Now this principle states that अब अगर ये जो आपका reflect और transmit part हुए थे, अगर आप उनकी direction reverse कर दो तो आपको exactly सिर्फ ये वाली जो light है वो मिलनी चाहिए, या simply आपको ये वाला जो amplitude है वो मिलना चाहिए, उसके अलावा आपको और कुछ नहीं मिलना चाहिए. This is what this principle says that. So now in the second stage, when I'm going from here to here, okay, I'm applying this principle. I'm saying that let us reverse the direction from here to here. Now, when I reverse the direction from here to here, this is now incident. T1 is the incident light from medium N2 to medium N1. And when you are going from medium N2 to N1, we said that R2 will be your reflection coefficient and T2 will be your transmission coefficient. तो इसका जो पार्ट आपका रिफ्लेक्ट होगा वो 8 टाइम्स T1 R2 हो जाएगा, क्योंकि एम्पलीट्यूड जो होगा ये इंसिडेंट है, उसको आपने रिफ्लेक्शन कोफिशिएंट से मल्टीप्लाई करा दिया. सिमिलरली जो ट्रांसमिटेड होगा 8 टाइम्स T1 मल्टीप्लाइड बाय द ट्रांसमिशन कोफिशिएंट एंड योर ट्रांसमिशन कोफिशिएंट इज T2. सो 8 टाइम्स T1 T2 आपका हो गया. नाउ if we apply the same principle on this one also, the reflected light, आपकी reflected light अभी तक इस direction में जा रही थी. Let's reverse the direction of this one also. Again, for this light also, there could be reflection and there could be transmission, both of the things. Now, if you talk about this light, this is the incident amplitude. ये अब आपका incident amplitude है. You are going from medium N1 to N2. R1 आपका reflection coefficient है, T1 आपका transmission coefficient है. तो जब ये AR1 अब इस डायरेक्शन में आके इसके ऊपर इंसिडेंट होगी तो इसका एक पार्ट जो है वो रिफ्लेक्ट हो जाएगा. इसका जो पार्ट रिफ्लेक्ट होगा A टाइम्स R1. इस पॉइंट पे व्हेन यू आर गोइंग फ्रॉम N1 टू N2 योर रिफ्लेक्शन कोफिशिएंट इज R1, तो आपके पास में सेकेंड टाइम R1 आ जाएगा और इट वुड बिकम A टाइम्स R1 स्क्वायर. जब ये वाली लाइट, हाँ जी,
can you please repeat what you said? Your voice was lagging very much.
Okay. Let me rub the second part. So I'll repeat the part for the second one. The first one was okay with you people. So I'll repeat now the second part again. So now we are saying that let us reverse the direction of reflected light also. अगर आप reflected light की भी direction reverse कर दोगे, so what would happen? ये यहाँ पे आके incident होगी इस point पे. इसका एक part जो है वो reflect होगा, एक part इसका जो है वो transmit होगा. हमको उन parts का amplitude find out करना है. अब अगर आपका A times R1 is the incident amplitude and if you are going from medium N1 to N2, तो जो आपका रिफ्लेक्टेड लाइट होगी, अगर ये आपकी इंसिडेंट है, सो and R1 is your reflection coefficient, तो आपकी जो reflected light होगी that would be A times R1 square. क्योंकि ये इंसिडेंट थी, इसको आप R1 से मल्टीप्लाई कर दोगे जो आपका रिफ्लेक्शन कोफिशिएंट है. इफ यू टॉक अबाउट द ट्रांसमिशन हियर, अगर आप ट्रांसमिशन की बात करते हो, A टाइम्स R1 आपकी इंसिडेंट है, आप मीडियम N1 से N2 जा रहे हैं, देन T1 इज द ट्रांसमिशन कोफिशिएंट. सो ये वाली लाइट जब इस पॉइंट पे जाके यहाँ पे रिफ्रैक्ट होगी, सो यू विल हैव A टाइम्स R1 एंड T multiplied by T1 because T1 is the transmission coefficient. तो जो इंसिडेंट होगा उसको आप ट्रांसमिशन कोफिशिएंट से मल्टीप्लाई कर देंगे. So this is how they will happen. The red one denotes what is going to happen with A times R1. आपकी रिफ्लेक्टेड लाइट के साथ में क्या होगा if you change the direction here, and the black one tells you what would happen with the transmitted light if you reverse the direction of the transmitted light. Now this principle said that you should only have A1. So that means if I add up these two terms now, अगर हम इन दोनों टर्म्स को ऐड करते हैं, A times T1 T2 plus A times R1 square should be equal to A. This is what it says, that we should get whatever we started with initially. So we started with initially a ray of light whose amplitude was A. In this first figure, there is nothing here. In the second place, we are getting this amplitudes here. So if it is true that अगर आप डायरेक्शन रिवर्स कर दो और एग्जैक्टली आपको सेम मिलना चाहिए, दैट मीन्स द सम ऑफ दीज टू टर्म्स शुड बी इक्वल टू 0. Because initially there was no ray of light at this point when this ray of light was incident. आपके पास में सिर्फ यहाँ लाइट थी और यहाँ लाइट थी. Now you are saying let's change the direction. Then this principle of optical reversibility says that you should get whatever you started with. उसके अलावा आपको कुछ भी एक्स्ट्रा नहीं मिलना चाहिए. So that means ये वाला जो portion है, we shouldn't be getting this portion, and which basically means that the sum of these two terms should be equal to 0. Now from here in this expression, A is the common here, can take that out. What you will get is T1 T2 plus R1 square is equal to 1. And let's call that equation 1. In the second case, A is common, T1 is common. R1 plus R2 is equal to 0. That means your either this term is equal to 0 or this term is equal to 0. This term cannot be 0. That means this term has to be 0. Because if you are saying this term is 0, either your A is 0 or your T1 is 0. That means either you are saying कि आपकी incident light ही नहीं थी. अगर incident light ही नहीं है, then nothing is going to happen. If you are saying T1 is 0, then you are talking about having something which is 100% reflecting, which is an extreme ideal case, which usually doesn't happen. So that would mean that the second term is 0. And if the second term is 0, this implies that R1 is equal to minus of R here. Now, and this is, let's call your equation number 2. Let's look back at this equation here. These are your amplitudes, right? And we know that energy is directly proportional to amplitude square, right? Your amplitude might not be conserved, but your energy is always going to be conserved, right? You can never violate energy conservation principle, because the fundamental physics says that you cannot create or destroy energy. You can simply convert it from one form to another form. So that means if energy is conserved and energy is equal to amplitude square, so that means आपकी incident light की जितनी भी energy थी, it is distributed between the reflected light and the transmitted light. And यहाँ पे हम amplitude की बात कर रहे हैं, and we say that your energy is directly proportional to amplitude square. So that means incident light energy would be proportional to A square, and that incident light energy has to be equal to the energy, sum of the energy of reflected and the transmitted light. So that means this has to be equal to this. And this is simply from the energy conservation principle. From here, then you can say that A square is common everywhere. You can say that 1 minus R1 square is equal to T1 square. And let's call that your equation number 3. Look at equation 1 and equation 3. Equation 1 says that T1, T2 is equal to 1 minus R square. This is your equation 1, which says that T1, T2 is equal to 1 minus R1 square. Equation number 3 says that 1 minus R square is equal to T1 square. So that means T1, T2 is equal to T1 square. Let me write this again here. You have one equation which...
Ma'am,
Hanji.
ma'am, how is it possible to have R1 plus R2 equal to 0? Aren't both of these terms positive in nature?
I'll just talk about that. I'll talk about the physical meaning of this.
Okay.
Yes. So your equation 1 says that T1, T2 plus R1 square is equal to 1. And your equation 3 says that 1 minus R1 square is equal to T1 square. So from here, in this equation, I can then say that 1 minus R1 square is equal to T1, T2. If left hand side of these two equations is equal to each other, that means right hand side also has to be equal to each other. What would that mean? That is your T1, T2 is equal to T1 square. Or you can say that T1 is equal to T2. Physically, what does this mean? This means that if you are going from, and let me draw a new picture here, and if you are going from medium N1 to N2, and your R1 is equal to minus R2. Physically, this says that if you are going from medium 1 to 2, and let's say 20% light is reflected and 80% light is transmitted. If this is your incident light here. That means if now your light is incident from N2 to N1, your reflection coefficient, amplitude is same. Sorry, magnitude is same, not the amplitude. Magnitude of reflection coefficient is same. That means again, there will be 20% light will be reflected and 80% light will be transmitted. Because you are saying that magnitude of T1 is equal to T2. Agar aap medium, remember T1 was the transmission coefficient when you are going from N1 to N2. T2 was the transmission coefficient when we were going from N2 to N1. So this means आप एयर से अगर ग्लास में जा रहे हो, अगर आपकी जितनी लाइट रिफ्लेक्ट होगी उतनी ही लाइट आपकी तब रिफ्लेक्ट होगी जब आप ग्लास टू एयर भी जाओगे. And similar is the case for the transmitted light. Now let's talk about this minus sign, which someone asked, and that was the main aim of doing this derivation from our interest. This minus sign basically tells you that there is going to be a phase change here. And that phase change is going to be a phase change of 180 degrees. Now, from the continuity of electric field and magnetic field at the interfaces, it was found that whenever you go from rarer to denser medium, जब कभी भी आप rarer से denser medium पे अगर आप जाओगे, there will be a phase change of 180 degrees, which basically means that if this is air, this is glass, अगर आपकी यहाँ पे light incident होगी और यहाँ पे जो light reflect होगी, उस reflected light का suddenly there will be a phase change of 180 degrees. वो with respect to incident light, it will be out of phase by 180 degrees. And that will only happen when you are moving from rarer to denser. अगर आप denser to rarer में जा रहे हो, तो again, if this is glass and this is air, यहाँ पे जो light incident आपकी होगी, there will be no phase change. So this light, let's say this is ray 1 and ray 2, there will be no phase difference between ray 1 and ray 2. But here in this case, If you are going from rarer to denser medium, there will be a sudden change in the phase by 180 degree at this point of reflection. And let me show you some pictures just to have a better representation of this. Now look at this figure here. So it's as if you have tied a rope and this end is a rigid end. अगर ये आपका rigid end होगा, which would basically correspond to the case when you are moving from rarer to the denser medium. Now look at this figure here. This was your incident light at this point. If you are looking from this side here and look at this point here in the same direction, you see that there is sudden jump of 180 degree at this point basically. And this is what meant by that your reflected light will have a phase shift of 180 degree. And you know that lambda corresponds to your 360 degree or 2 pi. That means if you are saying that there is a phase change of 180 degree or pi in the terms of the path length, that would correspond to lambda by 2 basically. And we are going to use this in our derivations that we'll do for the parallel thin film and the wedge shaped thin film. Let me show you this figure once more. Look at the rigid end. There is suddenly jump here. The rope came over here and then it just, when it was reflected, there was a sudden phase change here at the rigid end here. On the other hand, if it is the another case where this end of the rope is a free end, that means now we are talking about moving from here. We were talking about N1 being less than N2. So we were going from a rarer to denser medium. Now it is the opposite way around. And look at the expression here. What would happen? There is no phase change at this point. And here also, now the graph has been shifted a bit. So let me draw the point here. The reflected light and the incident light, they are in the same phase. There is no phase change. So that is the meant of the minus sign there. The minus sign basically accounts for the phase change that would happen if you are moving from the rarer to the denser medium. Transmission में ऐसा नहीं होगा. Transmission में चाहे आप rarer से denser में जाओ या denser से rarer में जाओ, कभी phase change नहीं होता है. And this is what has been shown in the coming figure here. Look at the rarer to denser medium. आपका transmitted still goes in the same phase as is the incident. आपका जो reflected है, there is a sudden phase change of 180 degree. Denser to अगर आप rarer में अगर जाते हो, in that case, the incident light will be reflected as it is without any change of the phase. But transmitted light में, there is never a change of the phase. That never happens in the case of transmitted light. And this is where the minus sign comes into the picture. An example of that is, for example, now you have glass here. Then you have air and then you have again the glass. So let's talk about this incident light here at this point. At this point, you are talking about going from glass to air. Glass is a denser medium as compared to air, so there is no phase change at this point. यहाँ पे आपका कोई भी phase change नहीं होगा ray 1 में. Now this is transmitted. Transmitted में कभी phase change होता नहीं है. At this point, when this reflection is happening from here to here, at this point your interface is from air to glass. So you are going from rarer to a denser medium. आप rarer से denser medium में जा रहे हो, तो इस point पे there will be a sudden change of 180 degree in your ray. And this ray too will have an additional phase difference of 180 degree. Or you can say that if you are talking about the path difference, we know that 180 degree corresponds to lambda by 2. So you can say that it would seem as if ray 2 has traveled an extra distance of lambda by 2. because of this sudden change in the phase at this point of interface. जो आपका 180 डिग्री का जो जंप हुआ है फेज में, उसको अगर आप पाथ में कन्वर्ट करना चाहते हो, then 180 degree is equivalent to lambda by 2. And which means that you can say that your ray 2 has traveled a distance of lambda by 2 extra as compared to ray 1, apart from this distance, which of course it has traveled extra. On the top of whatever is the path difference that you are calculating, in that you can add an additional of lambda by 2. आप जो भी कोई पाथ डिफरेंस इसमें कैलकुलेट करोगे, उसमें हम एडिशनल लैम्डा बाय 2 ऐड कर देंगे टू टेक इनटू अकाउंट दिस sudden jump in the phase or sudden phase shift that would happen when your light ray is reflected from a rarer to denser medium. And you need to remember that, because in your Newton's ring experiment, I think you might have done, some of you might have done that experiment, or you might be doing that in the near future. There is something like this happens there also, that there is a sudden jump in the phase or sudden change in the phase. So this is what it means physically. Hanji bache.
Ma'am, in the diagram, how can we show that ray 2 has lambda by 2 extra like part difference? How can we show it in the diagram?
In the diagram, you can only show the phase difference. You cannot show the path difference. क्योंकि आपका वेव बिहेवियर है वो रिपीटेटिव वेव बिहेवियर है.
ओके मैम.
तो या तो आप मतलब आइडियली ऐसा दिखाना शुरू करो कि ये वाली जो है ये आपकी रे यहाँ, इफ यू से दैट दिस इज व्हाट वाज एट टाइम t is equal to 0 and this was your ray 1, and then you say that your ray 2 had the additional this lambda by 2, and then you say that this is going to start from somewhere here like this. But here it is difficult to show क्योंकि आपका वेव बिहेवियर काइंड ऑफ रिपीटेटिव बिहेवियर है. And this lambda by 2 actually doesn't happen. Actual में आपका phase shift हो रहा है, not the path difference. ऐसा नहीं है एक्स्ट्रा जनरेट हो रहा है. हम वो phase shift को अकाउंट में लेने के लिए, अपने कन्वीनियंस के लिए, we are saying that let's put lambda by 2 over there.
Okay.
Okay. So this was all about the Stokes law. Now what we are going to do is the parallel thin film. I don't think I'll be able to finish the derivation, but anyway, let's start the derivation. So let me change the color. In the parallel thin film, what you are saying is that you have a film whose thickness is uniform. That means अगर आपकी यहाँ पे जो thickness है, let's say is D, it is D throughout the film. There is no variation in the thickness of the film. Now we'll talk about the interference pattern that could happen in this parallel thin film. Let's say you have air here. Let's say you have some medium here, and the refractive index of that medium is mu, and let's say you have air here again. You can of course take n1 n2 also, you will still get the same result. आप खुद से n1 n2 लेके देखिए, आपको exactly same result end में मिलेगा. Now let's say you had a ray of light incident here. A part of it will be reflected here itself. A part of it, I should have drawn the bigger picture. A part of it will be transmitted here. अब इस point पे again reflection होगा, इस point पे आपका transmission होगा. I am ignoring कि यहाँ पे आपका transmission भी होगा, यहाँ पे आपका reflection भी होगा, क्योंकि हमारा interest इन दो rays में है. We want to see what would be the path difference between these two rays. इन दो rays के बीच में क्या path difference होगा. Now, if you talk about ray 1 and ray 2, before we go into path difference, there is something called as optical path difference. You have a geometrical path difference. And then there is something called as optical path difference. It is nothing but आपका जो geometrical path difference है, you simply multiply it by mu, the refractive index of the medium through which your light is traveling. अगर आप ज्योमेट्रिकल पाथ डिफरेंस को उस पर्टिकुलर मीडियम के रिफ्रैक्टिव इंडेक्स से मल्टीप्लाई कर दोगे जिसके आप बात कर रहे हो, देन दैट वुड बी योर ऑप्टिकल पाथ डिफरेंस. And in this case, the optical path difference would be, if I can draw a perpendicular from this point on this ray, and let's say this is the perpendicular here. Now let's talk about ray 1 and ray 2. How much would be this path difference for ray 1 and ray 2? इस point तक दोनों ray जो थी वो single ray थी. So there is no path difference up to this point. Now here we have drawn a perpendicular and इसके बाद में ये दोनों रे हैं, they are parallel to each other, right? तो इस point के बाद में भी इनमें कोई भी path difference नहीं है after this point. So whatever is the path difference, that is only from this point and here to here. Now if you talk about ray 2 has from after this point, ray 2 has traveled this distance and this distance. ये वाला डिस्टेंस जो है वो आपकी रे 2 ने ट्रैवल किया है, रे 1 ने सिर्फ ये डिस्टेंस ट्रैवल किया है. तो इफ आई नाउ टॉक अबाउट द ऑप्टिकल पाथ डिफरेंस, and let's say this is your point A, this is your point B, this is your point C, this is your point D. For this medium, when your ray was traveling in this medium, your refractive index is mu. तो आपका जो इसके लिए optical जो path difference, sorry, this is the optical path, not the path difference. Ideally, even the difference is okay, but truly your optical path is equal to mu times geometrical path. Even the path difference is that basically means that this will propagate in the path difference also. ये आपके path difference में भी propagate करेगी. बट पाथ जो आपका ऑप्टिकल पाथ होगा वो म्यू टाइम्स ज्योमेट्रिकल पाथ के इक्वल होगा. तो अब अगर आप यहाँ इन दोनों रेस के बीच में पाथ डिफरेंस अगर कैलकुलेट करते हैं, देन रे 2 हैज ट्रैवल्ड दिस डिस्टेंस AB एंड BC इन अ मीडियम हुज रिफ्रैक्टिव इंडेक्स इज म्यू. तो ये वाली रे 2 है वो इतना डिस्टेंस ट्रैवल कर रही है. रे 1 की अगर आप बात करो, रे 1 ने सिर्फ ये डिस्टेंस ट्रैवल किया है इन एयर whose refractive index is 1. So your ray 1 will have the distance traveled this much. So this is the optical path difference between ray 1 and ray 2. Again I'm repeating that up to this point A ये सिंगल रे थे, DC के बाद में ये दोनों रे हैं वो एक दूसरे के पैरेलल हैं, एक दूसरे के पैरेलल हैं तो इक्वल डिस्टेंस ट्रैवल करेंगे. दैट मीन्स जो सिर्फ एक्स डिस्टेंस में जो डिफरेंस होगा वो आपका यहां से कंट्रीब्यूटेड होगा, यहां से यहां तक और यहां से यहां. सो दैट मीन्स आपका जो पाथ डिफरेंस अगर आप कैलकुलेट करोगे, ये वाली जो रे है ये एक ऐसे मीडियम में ट्रैवल कर रही है जिसका रिफ्रैक्टिव इंडेक्स म्यू है, ये वाली एक ऐसे मीडियम में ट्रैवल किया है जिसका रिफ्रैक्टिव इंडेक्स 1 है. तो ये आपका ऑप्टिकल पाथ डिफरेंस हो गया है. Those of you who are curious, can you prove that this is equal to 2 mu d cosine of r, where r is the angle of reflection and d is the thickness of this film? It's basic trigonometry. अब simple trigonometry use करके you can prove that this optical path difference is equal to 2 mu d cos r. एक बार खुद से try कीजिए. Nonetheless, next class में we'll do the derivation for this. Anyone has any doubt in today's class? Okay, so I'll end the class now and then I'll see you on Monday.